Right, this recording is to help you with lesson 5.03.01, solving linear trig equations. Alright, so we need to verify, first of all, that the x values are solutions. So to verify, we're going to plug that value back in for x and make sure that we actually do get 0 each time. So in part A, we get 2 cosine of pi over 3 minus 1. And so we know that cosine of pi over 3 is equivalent to 1/2 using our unit circle. So 2 times 1/2 is 1. 1 minus 1 does in fact equal 0. And the same thing for part B. Let's plug in 5 pi over 3. So cosine of 5 pi over 3, again using your unit circle, is 1/2. 2 times 1/2 is 1. So 1 minus 1 does give me 0. So all we needed to do is just verify that those actually were solutions. Right, if only things would stay that simple. Now let's actually solve for cosine x here. So to solve for cosine x, I would start by subtracting 1 from both sides and then dividing by 2. So now I'm going to use my unit circle. Where does cosine equal negative 1/2? Well, cosine equals negative 1/2 at 2 pi over 3 or at 4 pi over 3. Now it says we need to solve for we want every solution. Because you can go more than one time around your unit circle, we are going to add 2n pi after each one. This ensures that we get every single solution no matter how many times we are going to go around our unit circle. And the n can be any value, any integer value there. So it can be a negative number, 0, or a positive integer there. That's what n stands for, is any number that you want to plug in there, or any integer, I should say. I would say that most students forget to put in that plus 2n pi when they're solving equations. So don't forget that plus 2n pi at the end. Okay, here let's find also the solutions in the interval 0 to 2 pi. So I'm going to start by rewriting my problem. The cosecant x is the same thing as 1 over sine x. And then I'm going to get a common denominator so I can add those. I'd have to multiply each one by sine x, and when I do that, I get 2 sine squared x plus 1 all over sine x equals 0. I'm going to multiply both sides by sine x so I can get rid of that fraction. When I multiply both sides by sine x, I end up with this right here. 2 sine squared x plus 1 equals 0. My ultimate goal is to isolate sine x. So I would start by subtracting 1 and then dividing by 2. And then I get sine squared x. To get rid of a squared, I would think, well, I would need to take the square root of both sides. Right, but when I do that, I get the square root of a negative value. I cannot do the square root of a negative number. So here I know there's no solution. Right? And the reasoning they give is that 2 sine squared x plus 1 is always going to be positive value. Therefore, there's no solutions. Or it's always going to be greater than 0. So there's no solutions there. So either way you want to think about that is fine. The next one, there's so many different steps here, so I'm going to walk you through it slowly. The first thing we're going to do is we are going to rewrite cosecant as 1 over sine x and cotangent as cosine x over sine x. And then I'm going to add those fractions. When I add them, I get 1 plus cosine x over sine x. And I have that equal to 1. I'm going to multiply both sides by sine x so that I can get rid of my fraction. When I do that, I end up with this step right here. Now the tricky part is, how do I go from here to try to solving it? Well, I am going to square both sides. As long as I do the same thing to both sides, that's okay. So I'm going to square both sides, and I'm going to FOIL the left-hand side. So when I FOIL that, I end up with this mess right here. Okay? And it's not really a mess, it's kind of nice. And then what I'm going to do on the right-hand side, after I square that, is I'm going to use the Pythagorean identity, and I'm going to replace sine squared x with 1 minus cosine squared x. Because now I have everything in terms of cosine. I want everything on the same side of the equal sign, so I'm going to subtract 1 and add cosine squared x. And when I subtract 1 and add cosine squared x, I end up with this right here. And then I'm going to see, what do they have in common that I can pull out? They have a 2 cosine x in common. So if I pull that out, I'm left with just cosine x plus 1. All right. And here is where I'm going to take each part, so 2 cosine x, and set it equal to 0. And I'm going to take cosine x plus 1 and set that equal to 0, and I'm going to solve. So I would divide by 2, and that still gives me cosine x equals 0. And I'm going to subtract 1. All right, so where on the unit circle does cosine x equal 0? Well, it equals 0 at pi over 2 and 3 pi over 2. And where on the unit circle does cosine equal negative 1? That only happens at pi. So I have 3 values here for x. Now I always have to go back and check them in your original problem up here and make sure that it comes out okay. And when I check them into the original problem, I find that 3 pi over 2 and pi do not give me 1. Okay? So those are what we call extraneous roots. Okay? So really the only solution here is the pi over 2, because when I plug that back into the original equation, that's the only one that actually works. All right, my last one that I'm going to go through, I want to solve for x. So I'm just going to pretend for right now that I have cosine x equals the square root of 2 over 2. All right, and where does cosine of x, where does cosine equal square root 2 over 2? That happens at pi over 4. Okay, so if I were to have x equals pi over 4, remember you have to add in that 2n pi also, because we want every solution. So we're going to stick in that 2n pi there. All right, but I don't have just x, do I? I had x divided by 2. How do I get rid of that dividing by 2? Well, the opposite of dividing by 2 is multiplying by 2. So I'm going to multiply everything by 2. And when I do that, I get x equals 2 pi over 4, which is just pi over 2, plus 2 times 2 is 4 n pi. There might be times where you have to pretend it's just x and then go ahead and multiply your answer through by a certain number. Okay, and let me see here. Is there a certain interval? It's between 0 and 2 pi. So let's start sticking values in for n. If n equals 0, I get pi over 2 for my answer. And I want to make sure I hit every single answer in this interval. So when n equals 1, let's see, I get 2 pi over 2 plus 4 pi, which is really 8 pi over 2. So that gives me n pi over 2. Is n, or 9 pi over 2, sorry, not n pi. Is 9 pi over 2 in your interval of 0 to 2 pi? And the answer there is no, it is not. It's already on the outside. It's greater than 2 pi. So we do not include it in our solution set. So really the only answer between the 0 and 2 pi is pi over 2 in this case. Now, if 9 pi over 2 did fall in the interval, you would keep going with n. So I would do n equals 2 next, and then n equals 3, and then n equals 4. And I would keep going with those values for n until I finally hit a value that does not fall in my interval anymore. Then I know it's okay to stop. Okay, so it's a little bit tricky with those. So if you need help with those type of problems, make sure you come seek me out so that I can help you with those.